So hello to those who are watching in the future. Hello from the past. This is exam 4 review, and let's get started. So over here, chapter 8 is talking all about addition reactions of alkenes, and we know that alkenes are something like this that have a double bond on them. So I have over here that addition reactions are the addition of two groups across the double bond in the process of pi bond is broken. So there are a couple different ways that you can have these reactions go with. You can have them with a base, or you can also have them with a nucleophile. So just keep that in mind. And then at the end, usually we'll form like a carbocation intermediate step. That's kind of like depending on the reagents that we have. These are just a couple of names that you might want to look at, just to familiarize yourself with them. I thought that these would be important ones to know. So yeah, that's for that. Then over here we have addition versus elimination. So looking at it from a thermodynamic perspective, when we have addition reactions, it's pretty much the opposite of elimination. So addition reactions are thermodynamically favored at low temperatures, and elimination reactions are thermodynamically favored at high temperatures. So Dr. Dowdy could ask a question here like, if you were to lower the temperature of, you have like all three of these things, what would happen in the reaction, or what would the products look like? But he probably won't do something like that just because he only has like, what, 25 questions to test you on all of this material, but he could. So just, if it wasn't the book, it would be fair game. Now we're getting into mechanisms. So if you guys remember from the last review, I was talking about how we have like 4 basic things and the rest of Orgo 1 is based off of them. So we put those 4 things together and then we get all of these different types of mechanisms. So for example, one of the types is hydrogenation. And that's pretty much when you're adding an H and a Cl, Br, or iodine across the double bond. So like in this example over here, you have a cis alkene, and then you're adding HBr to it. And then at the end of this, you are adding a Br and then H. So something that we talk about here is things can be Markovnikov or they can be anti-Markovnikov. And so for this one, it's interesting because a majority of them are Markovnikov. So if you're doing something like HCl, HI, or HBr, then it's going to be Markovnikov. And if you don't know what that is, then I have this note over here. Markovnikov is adding the H to the less substituted carbon, and then your halogen or whatever, like the other half of it, to the more substituted. And then anti-Markovnikov is when the halogen is added to the less substituted carbon, and then the H is added to the more substituted carbon. But that's usually not as stable. So that's why a lot of these reactions will be doing Markovnikov. Usually if it is anti-Markovnikov, it's because the molecule is like too bulky to be put towards like a lot of other things, or that could be like one reason. So over here, just keep in mind that Markovnikov would be for HCl, HI, HBr, and then anti-Markovnikov can be found when you have HBr and then ROOR, or like ROOR. That's how I talk about this specific reagent, but I'm not really sure. Don't quote me on that. Just ROOR. But yeah, then I have some examples here of like what might happen. And then we have the mechanism. A couple of you guys were asking if we had to know mechanisms, and he did do an extra credit question, I think like a couple days ago, where he said what was the mechanism and the product. So I would just be familiar with what's happening in it. But if you are like on a time crunch, then just memorizing it should be fine. And just know that if it's going to be Markovnikov or anti-Markovnikov. Cool.
Wait, memorize what? I'm sorry.
If it's going to be Markovnikov or anti-Markovnikov, or yeah, pretty much just that.
Thank you.
But I would definitely, like, I drew out all of these nice mechanisms for you guys, so I would appreciate if you guys were kind of like looking at them at least, you know what I mean? So if you do have time.
Sorry, should we know like more of like the end product instead of like, because you're saying not so much of like the mechanism? Is that what you mean? Okay.
Definitely know what the end product is going to look like with the reagents. And Brittany made a super, super nice sheet for you guys. And somebody shared it in office hours. But I'm not sure. Let me maybe perhaps share it in chat if I still have it open. But I actually don't think that I do. No, unfortunately I do not. But if somebody wants to pull up that sheet that Brittany has, that one is really, there you go. Thank you to the one. That one is really, really helpful for just like reactants, products, what the reagent is, and any sort of like note about it. So yes, cool.
Thank you for drawing the mechanisms out. It really helps my understanding, by the way.
It helps my understanding too. So I was like, you know what? If it helped me, it might help the students. My pleasure. One more thing about hydrohalogenation is that the products form a racemic mixture. This is really important to know which ones form racemic mixtures, because Dr. Dowdy, although he is usually pretty nice about like not giving you answers that are like all the same but like kind of tricky, he could definitely give you an answer like, oh, this is A and then this is B. And then obviously answer C would probably be something like this, where he has Cl on like anti-Markovnikov, or something like that. So that's kind of like how he would have the options. But yeah, definitely know racemic mixture stuff as well, like which ones are forming racemic mixtures. Also, something to note is that these types of reactions can do carbocation rearrangements, and a lot of other ones can too. And if you guys remember from last exam, we kind of like were introduced to this concept, but pretty much it's when the carbocation moves so that it's more stabilized. So over here, you can see that it's moving from a 2-degree carbocation into a 3-degree carbocation. So then our product would be more stable at the end. So like this would be 60% of the product is forming this more stable one, and then 40% is forming that one. So he would probably end up asking a question like, oh, if you have this, what is the major product? And then the major product would just be the one where more product is being formed. Can rearrangement also happen with the acid catalyzed one? Let's see if I have that noted here, and if not, then we can look at the overall and kind of like draw our own conclusion. Over here for acid catalyzed hydration, hydration is when you add OH and H across the double bond, and there are 3 different types. So here are a couple of reagents that are like basic reagents would be like H3o and H2o, H2SO4, and they do the same thing. And we went over another reagent. There are a lot of reagents actually that will do the same thing, and that's why these reactions are so versatile. But usually in labs, they'll try and do the one where you have like the least amount of steps. They're like the least amount of work. So over here, acid catalyzed hydration, there's going to be 3 types. And let me scroll down to see if I have them numbered. One second, I'm trying to see, because 2 of them are Markovnikov, and then one of them is anti-Markovnikov. So this one is anti, because I just want to make sure that I'm telling you guys the right list of ones that do add water. And I'm pretty sure that one of them is just H2O, H2SO4, because that seems to be the reaction that's over here. I have not, unfortunately, posted the sheet anywhere. I was going to, but then I got very busy with physics. So, yes, unfortunately, but I will. By the end of the day, I will have it in your guys' group me. Is that cool?
Yeah, thank you.
Okay, perfect. So over here we have acid catalyzed hydration. It's just adding OH and H across the double bond. And then there are 3 methods. For acid catalyzed hydration, we have the addition of water across the double bond in the presence of acid. So over here, that can look like this, where we have H3o, or it can also look like this, where we have H2O, H2SO4. Just looking at this, where we're ranking the reactivity, we know which ones are going to be more reactive just because of the fact that the carbocation is going to be, it's going to be able to, let me think how to explain this. This one is going to be less reactive, and then this one would be most reactive because of the placement of the carbocation. And although the way that I'm understanding it in my head is that these other carbons would kind of be able to conjugate that plus sign, I guess that conjugation is making it more reactive in this case with the OH or H2O. So yes, in case he does ask a question like that, so over here it says like as stability increases, the reaction rate increases, which is usually like the opposite of what happens. So that is interesting.
As the stability of the carbocation, right?
Yes, as the stability of the carbocation. I think actually of the double bond,
okay,
which would also include the carbocation.
Okay, thank you.
So over here, this is what the mechanism looks like. Look how beautiful. Pretty much what's happening is that we have this double bond is coming and grabbing a hydrogen. Actually, I don't know why I didn't draw the arrows. I probably did that on accident. It's going to come and grab one of these hydrogens, and then these extra electrons are going to go to that oxygen, leaving us with this new hydrogen here. And this is a Markovnikov. So then we know that it's going to be added to the less substituted side. So like this is the more substituted, and then this would be like less substituted carbon. So over here it's being added to the less substituted. So we know it's Markovnikov. Then what is happening is that this water is coming and attacking this carbocation over here. But we know that water is a better leaving group than OH. And because we just added this on there, we don't want the water to leave, because I feel like water is, I don't feel like, that is how it is. Water would just be happier on its own than it would be connected to some like random carbon structure. So this other water is going to be like, it's okay, I'll help you guys out and take this hydrogen off of your hands. And so that's just like a proton transfer that's happening. And then we are left with our final structure. I also wrote over here that we have the proton, I like the steps for 1, 2, and 3. We have proton transfer, nucleophilic attack, and then another proton transfer. This intermediate right here that has the oxygen with a plus sign on it is called an Oxonium Ion. Not sure if that would be important. I did write it on there because I know that he usually does do a fill in the blank question. So if he did ask a question about that, I want you guys to be prepared. So then over here we have controlling the position of equilibrium. And this is, I don't think he would really test on this, but it was in your book, so he could. I also don't think that he really talked about this in lecture very much, But pretty much when you have dilute H2SO4, you're going to want to form that product. But if you have concentrated H2SO4, it is an acid. So it's going to more likely cause the breakdown of the product than it would form the formation of the product. Does that make sense?
Yeah.
Yes.
Okay. I have written over here that the breakdown of the addition product caused by concentrated H2SO4 is called acid catalyzed dehydration. So this is acid catalyzed dehydration, and it is an E1 mechanism. He doesn't really test too much about E1, E2 stuff anymore from my recollection, but when we go over questions later today, I will, or not later today, in like 30 minutes, then we'll see. Stereochemistry of acid catalyzed reactions. We have a race mixture, so then we have 50% of each of the enantiomers, which is just so nice for us. Okay, so then we have oxymercuration, demercuration, and is HD mercury? That would make sense, I think.
Yeah, that's
Yeah, it is.
mercury.
Okay, then the name totally makes sense here. I didn't actually think of that before, but this one is one of those mechanisms that you probably like don't have to know. But if you want to know it, then like more power to you. And personally, when I took the exam, I did know it because I was an overachiever when I took Orgo. But all of the will in my body to do anything in life left after I took Orgo 2. So I no longer, if I were you guys, I would just look at it. So here you are. Look at it with your eyes and call it a day. But let's look at what the products look like. So over here, we have a way to add water across the double bond while avoiding carbocation rearrangements, which is like pretty convenient. Let's see what I wrote while I was taking this. I said, I don't think he would test on this mechanism, but may ask for name of the intermediate products, most likely having reactants and products, then asking to pick the reagents. Be careful to see if a mechanism mentions rearrangement. So pretty much he would do something like, he would have this and then be like, how would I get to this product without having rearrangement? If I were Dr. Dowdy, that's how I would ask the question.
Oh, kind of like beginning and end and no middle. Okay.
I think a majority of the questions from when I took the exams were like that, where for this exam where he was having you like pick the reagents. He was also having me pick the products, but I feel like I remember the reagent questions more, like having to choose the reagents, just because they like traumatized me more than picking the products. So over here are some examples.
Nita, about like how you said like he might give you like the reactant and the product. Say if he didn't say anything about rearrangement, but it was like capable of rearranging and like the product wasn't rearranged, then you would just assume it's like oxymercuration.
I think that you would just have to assume.
Okay.
Good question though. Can an oxymercation demarcation also make enantiomers, or am I wrong?
Did it say that it could in the book?
Because I didn't really say anything about that. I don't remember. Because I just think if you're adding an OH, you could create like a Carl Sunderson could have it, but there is a bridge, so it is kind of confusing. Because I know it has to be like a backside attack.
Yeah, so
on that.
I didn't see anything about it forming an enantiomer, and also what's happening here is that we have like this plus sign is being distributed amongst two different things. And then I guess this carbon is a little bit more like electrophilic, so it would attack from, but it does kind of have, I'm not sure if for backside and front side attacks, if it needs to be a complete carbocation or if it can have a partial charge.
Wait, what do you mean? I kind of get what you're.
So you know how in order to have like this, we had like a full carbocation.
Oh yeah. So the bridge.
We
Yeah.
have it here instead of having a partial charge. So I'm not sure if maybe that even affects it actually. So I might just be like making that up. I didn't see anything about enantiomers being formed. So if there's an option on the exam that has one with enantiomers and like one without enantiomers, and it doesn't mention rearrangement, then I would probably just pick H3o or like H2O, H2SO4. That's what I would do.
Okay, because I was just wondering, because I know there's other mechanisms that create bridges and they can have like enantiomers, but I was just wondering if, because in the book, because I quickly looked through it, there is no mention of it, so I don't think I need to worry about it, but I was just wondering.
Yeah, I'm not sure because it wasn't in the book, and that's pretty much where I learned like 90% of the things that I know about organic chemistry. So Clutch says that it can form enantiomers. Okay, cool. Disregard anything I just said in the past 2 minutes. This one can also form enantiomers. Cool. Perfect.
For excuse me. For oxymercuration, like you said, if he like gets like, okay, what's the reagent to get us to like the last or to the products? Would like a good way to distinguish mercuration and acid catalyzation be like see if there's like any rearrangement? I don't know if you just said it. I know you said something about rearrangements, but like how could you tell?
I am trying to think of an example to explain it. You know how I had like this one here? Okay, so like this one did rearrangement.
Right.
But I'm guessing what would happen if we had something like this. So let's go ahead and take this molecule down, but then it would kind of be like, okay, so like the H3o product, oh my goodness, what did I just do? Okay, so the H3o product would probably look something like this because, yeah, then we are here, we add the hydrogen over here, we have our carbocation over here. Then for it to be tertiary substituted, it would go over here. And then we would add like our nice little water. But for this one, let's say that we're starting with something like this, what seems to be happening, I think our product would look different, question mark, because you wouldn't have rearrangement. So I believe that our product would just look like this.
Oh, okay. So I guess one way, if it was like, you know, fill in the blank or not fill guessing, it'll be a lot easier to see demercuration because like, oh, it's Markovnikov, so alcohol is going where it's more substitute.
Yeah. So in acid catalyzed, I think what's happening is that like just think of it as like acid catalyzed rearrangement can occur, and then in oxymercuration, demercuration, it just like won't occur.
Okay.
But it does say to avoid carbocation rearrangement. So I'm guessing that's what the product over here looks like, what's happening too. Cool.
Cool. Okay, that makes a bit more sense.
Awesome.
I hope he's not too mean about it, because I know
Yeah,
the problems can be a lot more trickier than they need to be.
definitely. So we're almost done going over the ones that I have. I think I have like a page left, or like a page and a half. So yeah. Then the next thing that we're going to go over is hydroboration oxidation, which is how you do the anti-Markovnikov addition of water. And this will result in syn addition as opposed to anti-addition. So over here we form enantiomers, and a lot of other reactions that we look at do anti-addition from what I've seen. Okay, let's see what everybody's saying. I'll look at the chat really quick. Yeah, he follows the book, so prob, don't have to worry. Yeah, his exams are pretty fair. There's never any crazy curveballs. LOL. Prob depends on where the OH is placed. Okay, I didn't even look like there were any questions for me, but I saw a lot of typing, so I just wanted to check that I wasn't missing anything. So yeah, a lot of the things that we see are anti-addition, but over here, we're gonna have syn addition. So pretty much when we're adding the OH and the hydrogen, they're just gonna be both added on wedges, or they're both going to be added on dashes. So that's pretty much what syn and anti-addition are. I'll show another explanation. Let me see if I have it open. Yep, so this is what syn looks like, and then this is what anti looks like. In case you guys wanted to write that down.
So just to like better understand, because I used to confuse myself. So for hydroboration, that one is anti, and it does, but not anti, anti-Markovnikov, but syn addition. So whatever we add to both sides is gonna both be on like a wedge or a dash if it's a chiral center. Okay.
And that's another thing. Make sure that it is a chiral center when you are doing your products, but again, it's multiple choice. So he probably won't even give you like chiral center options if it's not. So yeah, we went over anti-Markovnikov, and now we're actually going to be able to see it. So here we have BH3THF, and then make sure that you're choosing the ones that have numbers, and then make sure that you have like 1 and 2. And then, excuse me, the second reagent is going to be H2O2 NaOH, and the NaOH is what's actually going to add the OH on there. So over here we have our hydroboration oxidation mechanism. And again, we are forming this like, the first part is forming our, what is that? Boron? Bromine? I think that's boron, with like this, it's methyl chain on there. And then we have our oxidation part. Hydroboration and hydrogenation are both syn, and there is syn dihydroxylation, which is okay. Okay, and then we have oxidation as the second part, and that is, again, I wouldn't even know how to do this mechanism. I think of all of the mechanisms that you would look at and be like, I don't want to learn this, don't learn this one, because I've never seen him test on this. So then stereospecificity, we have syn addition. So again, both of them here are being added onto the wedges or on the dashes, or both of them are being added onto wedges like that. And then we have a pair of enantiomers, and then EE, I think that's enantiomeric excess or something like that. I feel like I've seen that term on an exam before, but it wasn't like important to the question. It was just like being tested on. It was just like extra information you didn't need. he would test on the product and stuff like this, because obviously hydroboration oxidation is the only way where you can do anti-Markovnikov addition of water, and that can be important for a lot of different mechanisms. But he probably just like wouldn't ask about the actual like, oh, what does it look like? What is the mechanism and product for this reaction? It says that you need to know the mechanism for this one on the announcement. Okay, kind of just.
Brittany said the same thing though, that we probably wouldn't need to know the mechanism.
Yeah, I've never seen him test on this particular mechanism. He's probably just look at it. This is another one where I would just look at it.
Yeah, it's too long.
Yeah, it is very long, and there's like, it literally in the book it says like this step repeats 4 times. Okay, like, anyways, so this is an example of what a product could look like, which is just like so extremely beautiful. Then we have catalytic hydrogenation. Catalytic hydrogenation involves the addition of molecular hydrogen, which is H2, across a double bond in the presence of a metal catalyst. So a metal catalyst can be something like PT, and then there's a couple other ones that I'll mention in a second, but just looking at it, we have 2 hydrogens and then our nice little metal. And so yes, this part in the book, it mentioned a lot of stuff. Is that what he wrote on the announcement about the mechanisms to know?
That's what Brittany recommended.
That's what Brittany recommended? Okay. Yeah, if Brittany says that, then most definitely know those and kind of just like be familiar with the other ones. So over here, this is like the formal definition, but in reality, what's happening is it's really just like getting rid of the double bond. But he could definitely ask like what happens in each of these reactions, which is why I was writing that down. This part of the book was talking a lot about what the products look like, because if there are like no chiral centers, then the syn addition part of it is like not important. If there's one center, then the enantiomers are formed, but like there can't really be, I guess there is syn addition, but both of the enantiomers are formed, and then for 2 centers, you need to have syn addition even for the enantiomers. So then that's when we're forming like a racemic mixture type of thing. And then, so this is what the products look like. This is one of those ones again where I'm talking about like kind of just the examples. Like I don't even think I wrote the mechanism. Yeah, I didn't. I don't think it mentioned the mechanism in the book. So yeah, this is syn addition. Then it goes and talks about homogeneous catalysts, and those would be PT, PD, and nickel, and those don't dissolve in reaction medium, whereas we have heterogeneous catalysts like Williston's catalyst, and that is soluble in the reaction medium and also causes syn addition. So like over here, we have, this is Williston's catalyst. Know what this catalyst looks like actually, because I'm trying to remember. I think I got tested on this when I was in Orgo 1. Okay, I'm trying to remember if I was in Orgo 1 or Orgo 2 and I had to know this. I've definitely seen this on an exam before. I'm not sure. Okay, if you guys are like not sure about what I'm talking about, then it might be an Orgo 2 topic. Or it might just look really similar to another reagent, which is also something possible. But anyways, if he does tests on it, here it is in front of you. We have H2 and Williston's catalyst, and that's causing syn addition, and the hydrogens are gone. There's no double bonds. So yeah, that's what I'm gonna say about that. I feel like I'm worrying you guys since you guys are like, wait, what is she talking about? PD CaCO3. Yeah, that's Lindlar's catalyst. So yes, this is the last page that I have, and then I got really busy this week. So let's finish going over this and then practice problems. And then from that, we'll be able to learn a lot of the other reagents that we haven't covered. And then I promise I will send this by the end of the day. So here we have halogenation and halohydrin formation. Halogenation is the addition of H2, and that includes Br2 and Cl2 across an alkene. Doesn't include iodine for some reason. So I don't remember why. Then we have, this is going to happen, anti-addition. And then the book talks about an exception that I'm not sure if you guys actually need to know that much detail about it, but it does talk about an exception. So over here, what's happening is we form this nice little like, what is this, like a brominium ion or something like that. This intermediate is called something weird. And then over here we have anti-addition. So this is like, anti-addition over here. And for cis, okay, that's what it was talking about in the book. It was talking about how like for cis-2-butene, we have anti-addition, but then for trans-2-butene, it looks the same. Like it turns out to be syn addition. Okay, IC restrictive, which is why it doesn't happen, but it turns out to be syn. I don't think Dr. Dowdy would test on this, but we'll go over the questions of like things that I think Dr. Dowdy would ask.
I'm sorry, I just got a little confused. Like for
yeah, what's the question?
You know what, never mind. I guess when we do practice problems, it'll maybe make more sense. I was just kind of confused, like, wait, how did it become cis or trans for like the halogenation?
Yeah, quick question though. Would it not just produce one product? It would just be a methyl compound. So when it just produced one, like it wouldn't be the same thing as syn addition, but it would just be a methyl.
That is such an interesting question that I am just now making okay, this is exactly what the book said. So let's just go ahead and add a methyl on here. Oh, how beautiful. Organic chemistry. Look at that. Bliss. He said that trans produces one product. Did he really say that? That is so nice. This is what the book said. Then why did the book say this then?
I mean, sometimes he doesn't follow the book. Like same thing happened with like the elimination, substitution stuff. I'm not entirely sure.
The book said that it was meso, and I started making stuff up. Is that what happened?
You're right. It technically produces a syn addition. It's weird.
I really hope he doesn't test too much.
This part was, I would say, even for me, it was confusing. So like for this product over here, would it only form one of these?
No, it's like, so only in the example for like the trans 2-butene, only in that example, you'll have to like worry about doing it because that's technically a meso compound if you split it down the middle. So it's weird. Yeah, it didn't really mention like the thing, like the bicarbonate ring, and it only mentions like a regular chain. So I don't know if
it mentions the exception. I think this is in the book. I may have like read it wrong, but I thought like the trans was the only one that had like the trans 2-butene was the only one that had the meso, so it was only like one. But I don't know, I'm not sure exactly.
Yeah, like I have an equal sign here, meaning that means like they're the same thing.
The book it puts the equal sign, but then I also interpret it as like it produces one product because I think in the homework or something it was like one product or it was practice something like that where it wanted you to produce one product. So I don't know what it wants really.
Yeah, because these would be identical compounds because you're just like keeping the R and S configuration, even though it looks like it's like drawn differently. But I think for the rest of them, just like don't worry about that one. He probably won't test on it being a meso compound at the end. Cool.
Okay.
But at the end of the day, if let's say that if we see this question normally and one of the options has anti-addition with these beautiful enantiomers, pick that one, in my opinion, in my educated opinion. Okay, so then over here we have halohydrin formation, and that's the addition of our nice little halogens in the presence of water. And with that, we form one of the halogens being added on, as well as a water being added on. So pretty much what happens first is we're forming this nice little triangle, and then water comes to attack. It's like an avatar where like everything, they all lived in harmony until like Fire Nation attacked. But in this case, it's the water molecule.
Nita, I just looked at the book, and I think the book is just basically saying that if it's like the cis with the 2 wedges, then that means it's meso, and if it's trans, it's meso, because it's in parentheses, but I think that's what it's saying.
I'm gonna look at the book. It says that the cis is meso too.
No, like, cause like you know how like the meso that you have with the 1 wedge and like the 1 dash, like that one's trans, but the one that you put it equal to is cis. So like the cis one is a meso compound, but so is the other one. So they're basically like, it's basically like 2 different forms of each other. I think that's what it's like implying.
Yeah, aren't
It's
they
like,
elliptical?
yeah, I think that's what it's trying to say, but it wrote it weird because it's in parentheses.
Since we're all so confused about it, I would say that it's safe to say that Dr. Dowdy would not test on this. That's my final conclusion about this question. I think that this question is too complicated for him to test on. This is kind of like above the scope of this class. That is my final statement on this meso anti-syn addition of halogenation. So, but if we see it on the practice problems, then we can draw another conclusion. But moving on, because we have 5 minutes before we have to do practice problems, we have anti-dihydroxylation. Pretty much what's happening here is that we have 2 OH groups and then an enantiomer is being formed. This is another one of those like crazy mechanisms where you form like an epoxide, and then over there's like, I don't even know, like a carboxylic acid and like a bunch of crazy stuff. So over here it says that the reagents determine if the product is syn or anti. But for the most part, this is what like a majority of things will look like. Like that one is going to be anti. Let's see if I have an example. Yes, I do. So like this one is CH3CO3H and then H3O. And those are the products that we form. Nice, all beautiful enantiomers. And then reacts with alkenes to form epoxides. So then RCO3H can also, like I said earlier, different reagents can do the same thing. So MCPBA and peroxyacetic acid also does the same thing. Then we have syn dihydroxylation, because that was anti-dihydroxylation. We have a lot of different reagents that can do the same thing. I know that OSO4 does something different though. But just for like, oh yeah, so OSO4 reacts first, forms this like nice little, I don't even know what this shape is, like a diamond shape, pretty. And then you react it with either one of these to form SYN. And then I have over here that KMNO4, it's a strong oxidizing agent and may further oxidize. I can't even read my handwriting. Acid, maybe. So you use OSO4 for SYN instead. Any questions?
So I guess to like sum everything up, or I tried to. So the reagent is the RCO3H, and also is that ML or MC? PBA, or is it MCPBA?
MCPBA, yeah.
Oh, so those two will give us the anti-addition of the two alcohols, and that'll always have an enantiomer if it has the chiral center, right? And then SIM is just the complete opposite, and the reagents for those is just the KMNO4 and everything else, like OSO4, all that.
Yes, perfect.
Don't need to know the mechanism. At least just that what I just said is like a good start. Yeah. Okay, at least for this.
Definitely what you said was a great start. So let me pull up my practice problems for you guys now. We have a lot of stuff to get through, so hopefully we're able to finish everything. Let's see. Oh, no, they definitely are important. I just didn't have time to finish going through them. Most definitely, all of the sections are extremely important. Again, yeah, definitely know how to do like everything. Was tert butoxide more like last exam stuff?
I think it came up like a couple times, but I think that might have been in chapter 9 actually.
Okay, never mind. This is an elimination question that I'm looking at. So then, bromination of propene. Okay, that one is fun. So this one, all of you guys should know. So let's go ahead and do this question. I can't wait because we were just talking about how like let's not even look at bromination questions. So are you guys ready to have your dreams crushed? So let's do this question over here. Which of the following species is the intermediate in the bromination of propene? So let's do A, B, C, or D? What do you guys think?
I'm thinking C or D, but I'm leaning a bit more to C. But I'm not entirely sure. I know there's a bridge for sure.
For sure, there's a bridge. So pretty much the answer here is going to be C, and what's going to happen is that this Br would come and attack this carbon so that these electrons can go over there so that we can get a final product of this. Does it add cis or syn or anti for Br? I think it was
It's anti.
Yeah. So then Br would be there. Cool. Okay, I'm trying to see if this is actually how the carbons would look out. So we have like 1, 2, 3. This would be like 1, 2, 3. I don't think that there would be another methyl there. Okay. Any questions? So we should know the intermediates, but not necessarily the mechanism. For this one, you would technically have to know the mechanism. Like there really wouldn't be a way to know. So this would have a wedge and a dash. Yeah. But also another way that you could just draw it is like trans like that. I'm pretty sure. And then like, this one is not chiral, yeah, over there. That is true. And then this would be a CH3. I'm trying to think. This is how another way that you can write as, and no, that's actually not a way that you can write as trans. Yeah, so because the other one is not chiral, it just wouldn't be, that's just not how it would work. So yes, that is my final statement on that. Which of the following is the correct mechanism for the elimination reaction? Okay, this is an elimination reaction. Okay. Next question, which set of reagents would be the best choice for the transformation shown below? Feel free to put your answers in the chat while I write. Here we have a Br, an OH, A, 1 is Br2, 2 is NaOH, B, we have 1 is HgBr, 2, H2O, 2 is NaBH4, C, we have 1 is BH3, 2 is Br2, 3 is NaOH, H2O2, D is Br2, H2O. We have a vote for D, another vote for D, and a verbal vote for D. Congratulations, you guys all get a 100 on this question because the answer is D. A lot of these other ones are really just like complicating it, and they really just wouldn't do that product. Yep, this is Halohydrin. Increasing stability. Did you guys do like stability of alkenes at all? Okay, I saved the best answer for last in that one. No, so you guys don't want to do stability of alkene question? Okay. It's on the exam, I asked you guys, so. No, I'm kidding. So why not, like, okay, fine, let's do it. We'll make this one quick. So rank in order of increasing stability. That's what I'm saying. Here we have 1 pentene, 2 is E, 2 pentene, 3 is 2, oops. Oh, that's actually a Z, 2 pentene, and 4 is 2 methyl bute 2 ene. So then let's go ahead and look at these. 1 pentene looks like this. E 2 pentene looks like this. Z 2 pentene looks like this. And then 2 methyl bute 2 ene looks like this. 2 methyl bute 2 ene. Okay, so looking at the most stable one, let's write a note for ourselves really quick, is that, okay, but it says rank in order of increasing stability. So cis,
Would it be, like, I guess if I was going backwards, would it be 4 first? Or I mean, I guess for the very most, okay, cool.
Yeah, so this is the most stable, that's correct.
And then would it be 2? Like after 4? Because you just said 6.
Yes.
And 3. Okay, I see what's
Second
going
one.
on with this. And then 3, 1.
3, and then 1 like that.
I'm gonna
Perfect. Yep, this is exactly how the stability would go, because even though this one is more on the outskirts than this one is, this one has a lot of like hindrance on it that's making it really unstable. So something that would happen is it would probably end up reacting just because it wants to get out of that environment. So yeah, this is the final answer for that one. Good job. Hopefully you guys have a question like that on your exam now that we've done it.
Oh, wait.
Yes.
I got confused. Sorry. So, but you just said 3 has like more hindrance. So wouldn't that make it like less stable than 1 then? But
Okay, my bad. I totally explained that incorrect. Yeah.
sorry.
This one is more stable because it has more substitution on it. My bad.
Okay, that's what I was thinking.
That was just how I was thinking in my head, but then I was looking at the answer and I was like, wow. Again, I think Dr. Dowdy is pretty nice with these questions though. So he wouldn't even give you an option with like 3 and 1 mixed up. 1 is the least stable because you know how in alkynes, this hydrogen is like so super acidic and wants to leave the situation because this carbon over here is trying to like stabilize all of these electrons. So then none of the electrons are like in this bond over here. So the hydrogen is just like, I want to leave. Kind of a similar thing is happening over here, but just on like a less serious note, where this carbon is starting to become like partially positive because it's having to, or not partially positive, it's kind of like trying to pull some of the electrons from this bond. So like if we were looking at like an electrostatic map, it would look like this, and the redness would be like a lot over here, if that makes sense. So it's, this hydrogen would be like more acidic and making it less stable than this one, where this one has like more things that are able to stabilize it.
Oh, so okay, so just kind of look at how much things are surrounding it, or substitute. Yeah, that. That's what I was thinking at first. Okay,
Yeah, pretty much.
thank you.
Okay, no problem. So this is, what is the product of the following reaction? So fun. We have CH3OH, 2 H2O, and then our options are this, OH, oxygen with a methyl, add a 1, 2 is this, and we have oxygen like that, oxygen with a methyl like that, 3, oxygen with a methyl like that, OH, OH over here, or 4, where we have oxygen like that, a wedge, and then that. So pretty much what's happening here is that this is what our reaction mechanism looks like. Even though the H would also come and attack it at the same time with it, eventually it would leave. So you can kind of just draw it like that for the sake of time. It's going to go ahead and attack the less substituted like that. And then we're giving the oxygens like that. So for regio selective and stereoselective product, we are looking for something that is trans. This reaction is very fast. If you add OH, it will affect the reaction. And then here we have Halohydrogenation. So what do you guys think the answer is?
Correct me if I'm. Wait, I think you just said it. I was thinking this was gonna be sim sim dihydroxyl. I don't know if I'm saying it right. Sim dihydroxygenation or so. Am I wrong? Or I guess I'm getting.
Dihydroxylate. Oh, the thing that we just did. This one.
Yeah, we're looking at it. I recognized it was. Oh, it's anti. Okay. I see it was on. So that's anti. Okay.
Yeah, so we have like our CH3OH or ONA, something like that. Cool.
Oh, okay. Then that makes it easier to see. Okay.
So the product would be, drum roll.
What is?
Would it just be the fourth one?
Yeah, it would be the fourth one. Perfect. Because over here we have trans, and then it's also attacking the correct
How come it's not
carbon.
3? Out of curiosity.
Mm-hmm.
I thought you were adding 2 alcohols.
Yeah, so over here, this reaction, if we were like actually to draw it out, it would look like this. So we have this and our OH, our oxygen, and then also this that's connected to our oxygen. And then this happens, this with a hydrogen happens, but then it's like super unhappy in its situation. So then this is what the products look like. I personally like drawing this out like this, but here we have our O connected to a hydrogen, also connected to a methyl, like that. So the oxygen goes and connects like that. And then we have a plus sign on here. And now we have this negative sign over there. And this is an Orgo 2 thing. But sometimes something that happens is that something that's on the same molecule can grab hydrogens like that. I'm not sure if this is exactly how that would happen, or if there would be like a water involved to come and like, or like an OH to come and grab this and give the electrons there, and then also like an OH for like this one to come and grab these. But it doesn't really matter. It's just asking about the product. But at the end of the day, this is what's happening, where we have our OH, another methyl, and our oxygen and our methyl, like that. Cool. And it would probably be the water in this molecule, but just like to prepare you guys all for Orgo 2. Is this anti-dihydroxylation? It looks like it to me.
Okay.
Cool.
Yeah, okay.
Any questions?
Not really a question. I guess it makes sense 3 is also wrong because like the methyl was just like got replaced with like the oxygen too, so that wouldn't make sense. I guess. Okay, I just noticed that. Okay, thank you though.
Boiling point stuff, do you think that would be related to this exam at all?
No, I don't think so.
I don't think he mentioned it like once, not even in the PowerPoint.
Yeah, a lot of these questions we did last time. A lot of these questions that I have are all elimination examples, which is so strange.
Do you have any chapter 9 questions?
I do have chapter 9 questions, but I do think that they are on the other practice questions that I have. I'm trying to find, okay, so let's do like this one. For the most part, a lot of these that I have right now are going to be chapter 8, and then hopefully at 6:30 I'll find some chapter 9 questions for us. Let's do show the overall reaction for the formation of racemic 3-bromohexane from E-hex-3-ene. And we have 3-hex-3-ene, E-hex-3-ene, with HBr, and that is what is giving us this beautiful BrH. And then this is S3 bromohexane. And then we also have R3 bromohexane. Does that make sense? Or just adding HBr?
So
to
you
this
want
one.
to draw the mechanism or so?
Nope, this is what was being asked in the question. Yeah, on this practice test, the answers are what are in the boxes, which is strange because it's kind of like just a naming question now that I'm looking at it. But let's do this next question. That is a mechanism that says draw a detailed stepwise mechanism of the reaction below. Where here we have this with H2O, H2SO4, and OH. How pretty. Again, one of my favorite reactions or favorite mechanisms. Here we have HOSO3 is how I like to draw that out. This is going to come and grab this hydrogen. Oxygens go over there, leaving us with this. Is this Markovnikov or anti-Markovnikov?
Markovnikov? For acid catalyzed?
Yes, it is Markovnikov. Great. So then what happens is we have a plus over here. Oh, interesting. I guess it wouldn't even really matter in this case just because they have both the same stability, but I guess it's like more towards the inside then. And then what do we think is going to happen because it's acid catalyzed? And this is 2 degree, and then this one would be 3 degree.
Rearrangement.
Rearrangement.
Perfect. Yep, so we have a rearrangement over here happening. And now we have the plus sign over here and our new hydrogen over there. And then what's going to happen?
We're going to have a nucleophilic attack.
Perfect. We have our water goes on there. OH, H. And then our OH comes to grab this, or even our SO4, or our SO3 can come and grab this. Forming our final product. Cool. Oh, I drew it backwards, but regardless.
So far,
Nice.
Yeah. I know those were like one of the few mechanisms that we have to know for sure.
Okay, so these are some that I would know for sure then. Provide the structure of the major product. I would definitely know that mechanism though, that I just did. Are you guys able to annotate?
I'm don't think so. Since you're on your iPad, I don't know why Zoom doesn't allow annotation when someone uses their iPad.
That is strange. Yeah, I think that the settings change when I do meetings on my iPad. I want you guys to like start doing these in your head though, and then I'll you guys can hold up your answers maybe to your screen. Are you interested in doing that?
Sure, why not?
Okay. So there you are. I'll give you guys 2 minutes. And then I'm going to do 2 a little bit more difficult questions, probably ones that he wouldn't ask, but I have them. So, okay, time is up. That I feel like I'm doing the poll questions in class. Over here, the first answer is this. What does a triangle mean? That is heat. So yes. Over here we have a BR or a BR like this. Those are the products. Did you guys also get that? What is the reaction? Is that not in your book? Okay, then don't know it. It was in my book. Okay, but in case he asks about it, because you know he always can. He can, maybe he's testing on all of organic chemistry on this exam and not informing you guys. Who knows? Maybe he could be on your final, but I probably not. So just know the first one. Does the last one look familiar? That one kind of looks like an elimination one, so you probably don't even need to know that. So pretty much just know that first one that I did over there. Let me ask you guys a question. Which alkene reacts faster with HBr? Question mark, explain. Here we have the first one. A or B? Any guesses?
Would it be A?
Why do you think it would be A?
Well, I got one of those gut feelings. I know it's not reliable, but I can try to manifest a reason. Cause with the alkene, like the bond is not in the benzene ring. I feel like it would be a lot easier to have the reaction.
My bad, I didn't finish drawing it. Okay, now tell me.
So I'm gonna. Okay.
Resonance, like, does B have like resonance? Since, yeah.
Yes, exactly. So the answer here is going to be B. Reacts faster. Reacts faster because it produces a more stable product. And this last one here that I have, just 110%. I want every single one of you guys here to know how to do the reactions with H2O, H2SO4. Is that understood?
You want us to know reactions with H2O, H2SO4.
Mm-hmm. That's like one that I most definitely see Dr. Dowdy asking you guys on. Let me see this. And know that it can do carbocation rearrangement. Just like keep that in mind because he can definitely ask a question like that. Okay, now let's go to this next question that I have, which is making me wonder now that I'm looking at this, what do you guys even have left for the rest of this exam? Did you guys go over IR at all?
No.
No. Nope. Okay, well, IR is just so fun. So, did you guys go over keto, enol, tautomeric pairs?
Yeah, that's all in the 9th chapter.
Yeah.
Next chapter, okay. That will be on your next exam then. Okay, so let's do this one. This is a chapter 9 question. Which of the bases below would be strong enough to deprotonate a terminal alkyne? Here we have 1 NaNH2 is 2, NH3 is 3, 4, O, and A is 4.
Would it be number 1? Because it's terpio it's like bulky.
I thought it's 2.
So we have a vote for 1.
Unless I'm getting it confused.
In our book, it says
It is,
terpenoxyl and O and A are not strong enough.
yeah, because that's the oxygen. It's
Yeah.
not a strong base, so it's definitely 2.
Oh, okay.
Yep, perfect. There you go. So the answer is going to be 2. And this is another thing where bases are doing the same thing. So something like ONH or NaNH2 will do the same thing. And then they will give us a product like this. Do you think that he would ask you guys a question like a prominent, oh no, that's never mind. That is also the other thing for next exam. But I remember that question was so fun. So unfortunately, we will have to wait. What is the major organic product obtained from the series of reactions? The following series of reactions. Then we have this with NaNH2. Then we have this with Br, and then we have this with H2 and Lindlar's catalyst. This is 1. This is 2. This is 3. And this is 4. So I have a vote for 3. And let's go ahead and write some notes over here. So we have H2 Lindlar catalyst.
Wouldn't it? Oh,
Yeah, what's up?
no, because all I know is that with Linear, it like makes things into like alkanes.
Mm-hmm.
So I thought, oh, if it's like the very last step, wouldn't it all just be single bonds?
So H2 Lindlar's product turns a triple bond into a double bond and also yields a cis product. But if we do,
Oh, I got it confused with when there's metals then.
but if we do sodium in ammonium, like NaNH3, then we would get a trans product. Something like this, or a trans product, something like in 2. But if we do H2 and a metal, you get a single bond. A single bond. Something like 1. But in this reaction over here, we have this, where we have NH3 comes and we have this hydrogen here. Nitrogen is going to grab that hydrogen, give those electrons to this carbon. And then we have this nice little carbocation like that. Then what's happening is that we have this with the Br. This will come and attack this carbon, making the leaving group leave. Then we are left with something like this. Where it's just adding on. So you have to be really, really careful with what's happening here, because nothing is actually breaking the triple bond in this one. And then after the H2 Lindlar's catalyst, we get this. And what does that one look like?
It looks like 3.
Exactly. So the answer here is going to be 3. 300,000%. Dr. Dowdy could ask a question like this. If
So,
I were Dr. Dowdy, I would ask a question like that.
so what you did first was the sodium and ammonia, right? In there,
Yeah.
and it went to the carbon.
That's not ammonium. It's just NH2.
Oh,
I'm pretty sure ammonium is NH3 and ammonia is NH4. And anything other than that is just like NH2. Am I wrong?
I was just looking at what you wrote with the NH3.
Yeah, that would be if I use this in like instead of H2 Lindlar's catalyst. So if we replace like this for this, or we replace this for this, then that's when we would get a trans product, and that's when we would get a single bond.
Okay.
Does that make sense?
Kind of. I still need to
Kinda.
go some more chapter 9 stuff.
Does this stuff look like chapter 9 stuff?
Yeah, it really does.
Okay.
Lily talked about it and I thought I understood it. I guess since they only asked like, oh, they only asked for one way, it wasn't like, oh, a combination of two. That's what like tripped me up. Plus I went over it today before class.
It's okay, you guys have the rest of the weekend. So let's go ahead and do sodium and liquid ammonium, because I know that one can be a little bit hard. Ammonia to form trans 3-hexene. So A is cis 2-hexene, B is cis 3-hexene, C is 2-hexene, D is 3-hexene, E is trans 2-hexene. So this is what these are looking like. Shoot. Or we can have this, or we can have this, or we can have this, or this. And because over here we are reducing it, we're going to want to have our starting product obviously be something that is an ine. So right off the bat, we can cross out A, B, and C. So we have Na, NH3. We're trying to form this product. What do you guys think the answer is?
What if we do then? It's like, it's already like a 3-hexene or so.
Yep, exactly. Hopefully I forgot the X over there. Yeah, the answer there would be D. Do you guys go over IR on the next exam? Or is that the exam after?
Wait, what's IR again? We discussed it.
I don't even know what it stands for right now. IR.
Wait, does it have to do with like,
infrared.
is it like radical reactions? Does that have to do with radical stuff? If it's radical, then it's next chapter.
Yeah, radicals are next chapter.
Yeah, so I don't think.
Now, I don't know why I'm asking you guys what's on the next chapter, because we literally went over worksheets from the next chapter in our meeting today with the TAs. So just ignore me. Oh, this one, you guys went over oxidation reduction reactions, right? Oxidation reduction.
I think so.
I think so.
So many.
Let's just do it to be safe, because I feel like I remember him asking somebody like, what is a oxidation? And then somebody was like, oh, when you, they said the Gen Chem definition, and he was like, okay, but what about an orgo? So let's do classify as oxidation reduction for neither. I actually don't know how to spell neither, so let's just pretend that that's how you spell it for right now. But let's say that this is what's happening. So cute. And My favorite way to do this is to actually draw out hydrogens, count carbons, all of that fun stuff. So over here we have 2, 1, 1, 2, 2, 2, giving us C6, H10. Over here we have 2, 1, 2, 2, 2, 2, and then we have C6, H11, Cl. We have one more CH and one more CX, making this what type of reaction? I have a vote for reduction. Anybody else? Okay, maybe I just like won't tell you guys the answer then, huh? What do you guys think? Okay, I have a vote for neither. Jenna, do you want to tell me why you said that?
So this could be wrong, but I don't think it could be reduction since your H's are increasing. And I don't really know why it's not oxidation.
So the answer here is going to be neither. And that is because it's kind of like canceling each other. You can't have both of them happening at the same time, is the way that I understood it. Does that make sense? So like if both of them are happening at the same time, then you kind of just like throw in the towel and you're like, okay, never mind. Any comments, concerns? Over here for this one, we have one more oxygen. What do you guys think that one is? So if it was one more CH, we're about to do this one right now. So I'm just actually going to draw directly on this one. Here we have 1, 1, and 2 giving us C5H4O4. Here we have 1, 2, 3, 4, 5, 6 giving us C5H6O4. So we have 2 more hydrogens. This is considered reduction. My bad. This is considered oxidation. Obviously, you're adding an oxygen. And then this one where we have 2 more hydrogens, what is that?
Reduction.
Yep, perfect. This is going to be reduction. Awesome, you guys. Now, the way he would probably have this is as multiple choice, where it would be like A, oxidation, reduction, neither. B, neither, reduction, oxidation. And then you would just have to pick the one where they're matching up is what I imagine him doing. Have you guys learned the reagent PCC CH2Cl2? Have you guys gone over ketone carboxylic acid aldehyde reactions at all?
Yeah, today we did.
And it's on this exam?
I think so, yeah.
Oh, no way.
Yeah, I think he did a little
I don't think it was a poll question, but I think he did it might have been a poll question. I think he did a question on it too.
Involving triple bonds or like not involving triple bonds?
Let me look. Yeah, like he did one, well, he did two. Like he did which product would be isolated from the reaction shown, and it was a benzene ring with the triple bond. Well, no, that's not. Well, I mean, it
Like
had it.
this? Does that look familiar to any of you guys? Adding oxygens is oxidation. Adding H's is reduction. Adding like a mixture of the two is going to be neither.
Yeah, no, I don't think we've done that. He just did that.
Okay.
Keto, it's like the long word. It's like two words. Keto something. The keto enol tautomerization.
You guys did keto enol tautomerization today?
Yes. And then he had like the internal alkene and the terminal alkene with like one producing the ketone and then like the terminal producing the aldehyde.
Okay. But that's different from the other stuff that I'm thinking about. That's like, it gets a little bit more complicated later on. I think in the upcoming chapters. Let's do two more of these. Let's do three more questions really fast. Correct classification. Of this reaction. So we are going from 1, 2, 3, 4, 5, 6 to 1, 2, 3, 4, 5, 6 plus an oxygen. Okay, yeah. So we're adding an oxygen on there. Is this an elimination reaction where we have degree of substitution increases? Is this B, a substitution reaction where displacement of an atom with another atom? Is this C, reduction reaction, where we have decrease in the number of C double bond O. So it's decrease in the degree of oxidation. So we can have something like a C double bond O going to COH bond, something like that, with addition, or is this D, oxidation reaction? Wow, my handwriting is just not, this is an increase in the number of the triple double bond O bonds. What do we think the answer is? Yes, perfect. The answer actually is C. Thank you so much for answering the question. So here, that was that question. Let's do this one because I do want you guys to have a couple of these questions like with you. So let's do which of the following alkynes upon ozonolysis would be expected to form one product. And just by you guys being so extremely smart, how do you think we would do that? What would we need? Anybody? Would the bond be at the very end? That is a really nice hypothesis. Parallel center. So actually what's happening here is that we need to have symmetry. So that when we have whatever it is, it's able to just break it straight down the middle because of cleavage. Yeah, so our answer here is going to look like this. Let's say that we have our O3 with our H2O. We're forming our two aldehydes like that. See, this is one of those questions where, like, unless you've seen it before, it's really, really hard to even be able to answer it. So hopefully you guys see something like that on your exam. Which of the following, I'm going to do another one of the base questions, but this time mentioning pKa's. Strong enough to deprotonate a terminal alkyne. Here we have 1, which is NaH, 2, which is our nice little bulky base, 3, NH3, or 4, ONA. Here we have a pKa of 20. Here we have a pKa of 18. This is ammonia. Is that ammonia? The pKa is small. So this obviously is the answer because I told you guys earlier, and it's because has a good pKa. Normally in a alkyne terminal alkyne like that, the pKa is 25. And then I have written here that there are many ways to deprotonate it. So if you find this question on your exam, know that we need something like NaNH2, which is what we saw earlier, or something like NaH, so like sodium amide. And those are the questions that I have definitely 100,000% check out Brittany's review. I'm going to go ahead and stop recording. So thank you if you've watched this recording all the way through. Subscribe.